So my talk will be another repetition of FFT, and I will go back to start of FFT, so it will be lighter. So hope you will like it, lighter math. But I will add two add-ons. The first one is the term twiddle. And so does anyone heard of this term before? Nice, nice. So it does show up in the Circle-Stock paper from page 15. And when you search twiddle in FFT on Google, and most time you will find it is something related to digital signal processing, because FFT is originally from that space, right? And the FFT, you want to transfer digital signal from time domain to frequency domain. And twiddle, they use this term there. But nevertheless, I want to study it because it shows in STU implementation. And in STU implementation, in every prover instance, it's kind of a standard setup stage that you need to set up the twiddle. And so I think it's a good idea to have to know what it is at least. So this is the first term. And then the second thing I want to explain is butterfly. This is, anyone heard this as well? Nice. So it is a graph to visualizing the steps of FFT. So I want to introduce it because I think it will help to understand what is twiddle. So I want to start with something very simple, some math we know from high school. So I have a polynomial. I also want to use the example that people use most, 8 degree 7 with 8 coefficients polynomial. X 7 square 7. So I got this polynomial. This is the representation of the polynomial in the coefficient by coefficiency. And I want to transfer it to the evaluation representation, which means I want to choose 8 points in this polynomial and get their evaluations. Suppose this polynomial, we draw it, it looks like this. I just draw randomly. And so we want to choose 8 points and get their evaluations. So how should we do that? We have FFT, and FFT is actually doing this stuff. But now we are high school students, we don't know FFT. So we just straightforward choose 8 points randomly and then do the evaluations. This is the most hardworking way. So can we do something better? So before we do any optimization, I want to first actually simplify my problem. So it's the best way to solve a problem, to make your problem easier. I want to, instead of working on a generalized polynomial, I want to work on with some special polynomial. Simple one, fx equal to x squared. And with this graph, the question is, what point now should you choose to get these 8 points? Is there any set of points that when you know the value of the first point, you immediately implies that you know the value of the second one? So obviously we choose the point that they are symmetric to the y-axis, right? Because now if we choose fx minus x, we also know the evaluation of fx. Right? This is the property of even function, right? So now the next question comes. what if my polynomial looks like this? It becomes cube. And does the same trick applies as well? Yes, but with some caveat. Now we have f minus x equal to f this. This is the property of odd function. So now we get the inspiration from this. So now let's see, if we go back to this problem, what should we do? So we get the inspiration from there. We separate this polynomial to odd function and the even function. So let's start with even plus a2x squared plus a4x 2 plus a6x6, right? And now this is the f even x. I write x squared. And for the even function, it's a1 x1 a3x3 plus blah blah blah. So now I want to factor 1x outside of the odd function. So I do this. Here become 2. Let's write them out. x4 plus x7, x6, right? And now this one is f odd x squared. And now I want to write my original polynomial become fx equal to f even x squared plus x f odd x squared and f minus x equal to f plus x f minus, because now we are working on minus x, negative x squared. So you see that now we change our polynomial to 2 polynomial, but yep.
That one should be over. That's the second.
Yes. Thank you.
And also that INN.
Which one?
FO x squared A1 A1 plus
Oh yeah. Thank you. Yeah. Now we have we introduced 2 more polynomial, f even and f odd. With these 2 polynomial, their degree is actually half of the original polynomial, because now we are working on x squared. And so, summary, we introduced 2 more polynomial. This is extra work, but we have the degree. And what we gain is here, we have a lot of recycled computation that we can use. So now I want to generalize the problem even more. Let's say we have, now this is 8 degree. I want something that's very large, very large, and now these polynomials, they are still very high degree. And the good thing is my problem doesn't change. I still want to get a polynomial from its coefficient representation to evaluation representation. So I can do recursive step. I just start take this polynomial and this polynomial, start to split them again. Again and again, this is the recursive step, the mind of FFT. And now we see the problem comes if we are still talking about this space. because now if we want to, this is the first recursive. Now we want to do the second recursive, but here x squared can only be positive number. We don't have this pair of negative x and x. So we couldn't do the same trick as before. That's because the algebraic structure behind broken. And this is the point where in digital, I think the genius FFT idea comes. In digital signature processing is the point where they introduce the complex number I. And we are talking about the ZKP, then we're talking about this multiplicative group. So, yeah, so I think I covered the idea of FFT, and now I'm just going to draw the butterfly. We can erase this. So I want to start FFT with what I have and what I want to do. What is my goal? My goal is I have, what I have now is the efficient, the coefficient. And my goal is to compute, let's say now I'm working on the multiplicative group. Start from omega 0 and omega 1. I think I kind of need to write them all. 2, 3, 4, blah, 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 7. And so this is what I want to compute. And how I want to compute it, I use the same inspiration. So for the next step, I start to do the split of the polynomial. So the first value is equal to f even omega 0 plus f odd omega 0. This should be square, but then it gets the same value. Then I have f1 is also f even f square plus f odd. Here should have an extra omega because I'm working.
Omega 0.
Here, yes. Yes. And omega 2. And then I think I can maybe ignore the others and now come to f omega 4. Here we started to use the trick we discussed before, f omega 4, and when you square it, it becomes f omega 0, right? And then here we need to plus the inverse of omega, f odd omega 0. That makes sense? My intuition is I really want to write here minus omega. Is that correct? Minus omega, because if I use the same inspiration here, it's really kind of intuitive to here I started to, instead of writing this, and write minus omega 0 But I think it's wrong. I need to write in the inverse of.
Why? Why use inverse instead of multiplication?
Because it's the group multiplication. The multiplication group operation is a multiplication. And now if, no, it's multiplication. If I write here minus, it kind of means omega 0 is equal to minus omega 4. No, omega 2. So,
Okay, inversion is a multiplicative inversion, right?
yeah.
Okay.
Yeah. Yeah, the problem I think I don't understand is, can I write something like this omega is equal to minus omega to the power 4?
Yeah.
You can?
Yeah.
I can, actually.
Yeah.
Why?
You could. Because omega to 4 is negative omega.
But then this is the addition. You have this. Then it means this omega 4 is the inverse of addition operation of omega.
Okay. The inversion, the multiplicative inversion of omega is omega to 7.
Omega to 7.
Yeah. Right? Because for multiplicative inversion that omega plus omega times inversion of omega equals to 1.
Yeah.
So
yeah.
that the multiplicative inversion of omega is omega to 7. Is
Multiplication.
right? Because omega to 8, omega is the 8th use of unity, right? So omega, the least number of exponent of omega is equal to 8. So omega 8 equals 1.
Yeah.
Then inversion of omega equals to omega to 7.
The inverse of omega is
Omega inverse, right? Equals
yeah,
to
omega
to
7.
Yeah.
And
So here you use inf function. So is it multiplicative inversion or additive inversion? So it is a additive because now right now the domain is a multiplicative group. So I think that here the inversion is a multiplicative inversion.
Multiplicative
So here
inversion.
the omega should be omega to 7 if you use inf.
So yes.
But the negative omega is not equal to inversion of omega. Right.
Yeah. So this actually correct. I can
Yeah, it's
write
correct.
like
That's correct.
okay. Yeah, this counts. Thanks for the explain. Okay. Okay.
3 minutes.
Yeah. Yeah. So now we start to see the repetition of the equation, the values we can repeat the use. And then I continue here, I don't write them all, and continue with this. Now we transfer these values to more polynomials, and still two more polynomials, but each polynomial we only evaluate on 4 points because we use the repeated values. So we need this one, and this one, and on others. And continue from, we compute this one first, Fe omega square. I start doing the split again. This this even function split to more even function, and then plus omega. Even odd 0, and this is the second layer. And then I continue from, it's the same thing here, like you do split. To the end, it become, I need to compute this one. Even, and also even, odd. And this one, what is this function actually? So this function means we split the coefficients 3 times. So the first one we split to from 8 to 4, and these 4 coefficients is here. And in FE we have A0 and A4. A0, A2, A4, A6, and F even we have A0, A4, and F even is A0. So this eventually become A0. Too much? Okay. And then this one is actually A4. And now the bit reverse order comes. So at the end, you just, all the efficiency you get is A0, A4, A2, A6, A5, A7, 3, A7. This is a bit reverse order of the coefficiency.
Actually, EEO is not 4, right? EEO is 1. EEO is 1.
But this FEEO is come from FEE, right?
Yeah, I think E stands for 0, so EO means 0, 0, 1, so that one should be 1.
Isn't it reverse?
So finally, that one should be the reverse result.
You're talking about this one, or?
I think it's fine. It just depends on how the order you're writing down the notion. It's fine, I think.
Yeah, let me quickly introduce the.
You don't have time.
Okay, let's tell them. I still didn't say it. Yeah.
Yeah.
Yeah,
we
okay.
have time.
Okay. Thank you.